Hi everyone, welcome to our second video on the TBarrier tutorial. So in the first video, we basically I gave an introduction to the purpose of the software package, why it was developed, and we also saw how to download and install the Conda environment together with all its necessary packages. Now, in the second video, we will go through the structure of the TBarrier notebooks, and especially the structure of the whole folder, so that you can then eventually use them for your research or educational purposes. So in the previous video, I downloaded the TBarrier folder and I placed it on my desktop. So it will, for the remainder of this tutorial, it will always remain on my desktop. And we also saw how to install the Conda environment. So as I said in the previous video, the first thing we do whenever we open and want to run our notebooks, we go to the terminal and activate the environment. So we type in Conda, activate TBarrier. What this does is it switches from our base environment to our TBarrier environment. So once we're on a TBarrier environment, we can run our notebooks. So what I generally tend to do is after activating the environment, I just type TBarrier Notebook. So what this does is it opens a browser. So this browser contains various folders. Since I placed my TBarrier folder inside the desktop or on the desktop, I will navigate first into the desktop and then to the TBarrier. Oh, sorry, that's too much. So now I'm inside the TBarrier folder. This TBarrier folder contains a bunch of other files, such as another TBarrier folder. So this TBarrier folder, which will essentially be the core of our repository because it contains all the data, the notebooks, and all the necessary functions to compute various quantities. Other important files that we already saw are the environment.yml file or the requirements.txt file. So in the last video, I showed you how to install the environment using the environment.yml file. However, one could also use the requirements.txt file. So in fact, if I open the requirements.txt file, then you can see that I got a bunch of files here. A bunch of packages which I would need to install in order to run the notebooks. Then it also contains an installation.markdown file, which simply goes through installation steps. But you don't need this right now because we already went through it basically in the previous video. So let's inspect now the core of our repository, which is inside this TBarrier folder. So if I click on it, then I can see that there are two other subfolders. So one subfolder is designed for 2D velocity datasets, and the other subfolder is designed for 3D velocity datasets. Now, I decided to split the notebooks and the demos in 2D and 3D simply because it's easier to compute functions with just 2D datasets and functions which exclusively deal with 3D datasets. I think it's better to separate these two things. Of course, the function. So if I want to compute the velocity for the 2D dataset or for a 3D dataset, the functions will be related, but they will differ slightly. So that's why I prefer to separate them from the beginning. However, the 2D folder and the 3D folder are essentially structured in the same way. So there will be no difference. In fact, if I click on a 2D folder, the 2D folder contains 3 subfolders. So one subfolder is called data and the other two are demos and subfunctions. So we start with the subfunctions folder. The subfunctions folder contains only functions. So no computations are performed in this folder. It just contains scripts which have all the functions. So if I click on subfunctions, again, with 2 subfolders. So one subfolder, which is called integration, and it contains all the scripts and functions which have to deal with integrating particle trajectories. So of course, we'll find one script, which is called integration/dfdt. So what this script does is it simply defines a function, which is this one here, our main function, which computes the trajectory for a specific particle starting at a certain point in space and time. The other function which is inside our subfunction folder, our integration folder, is the velocity function. So as you can imagine, this script simply contains a function, def velocity, which simply computes the velocity of a particle at a certain point in space and time. And we will not extensively treat them right now. We will go through them in the next videos, but we will just like keep track of the fact that the subfunctions folder contains a folder which takes care of all the integration, and another folder which is called utils, which contains scripts which define functions for very basic computations, such as computing the grain of the velocity field, computing the eigenvalue of the symmetric 2x2 matrix, or computing the grain of the flow map. So these are all very basic functions that we will then use in our notebooks. However, I decided to keep them separate. So I have one folder which is called subfunctions, which just contains really functions, and no computations are done here. It's just like defining functions which are then called in our notebooks. So where are our notebooks stored? Our notebooks are stored inside this demos function. So inside the demo function, we will file all our notebooks. And in fact, we decided to split this demos function into various functions. So active barriers basically contains all the notebooks which have to do with computation of active barriers in 2 dimensions. Advective barriers contains all the notebooks which have to do with computing advective barriers in 2 dimensions. Decompositions, what is contained inside this folder is simply, it shows you how to do some basic computations, such as computing doing the singular value decomposition, polar decomposition, and so on. Then we got a folder which is called diffusion barriers. Again, it contains all the necessary function for it contains all necessary notebooks related to computing diffusive barriers in 2D. The same holds for stochastic barriers. And then we got one folder which is called introduction. So what I will be doing inside this folder is I will show you so this folder contains notebooks which show you how to compute very simple quantities, which we will then use in the other notebooks. And these simple quantities will simply be, okay, I want to compute the velocity, or I want to compute the trajectory, I want to compute the gradient of the flow map, I want to compute the Cauchy-Green strain tensor. So inside here, we will have like notebooks which do very simple computations, which, however, we will then use in all these more advanced notebooks. So eventually, what we'll be dealing with in the next video is we will take a look at this introduction folder, and we will start running the computations. So we will start then computing the velocity, computing trajectories, and computing gradient of the flow map, for example. So we'll start doing these very simple computations so that you get a feeling of how to use these functions also for your own research. Of course, you can then start making adaptations to these functions once you have an intuition about how they work. Now, the last folder I have to consider is this data folder. So as you can guess, this data folder contains all the necessary data that, or a bunch of data sets that will be used in our notebooks. So these data sets are generally fairly commonly used data sets, especially in our group. So these are fairly often used in our papers. We decided to pick 3 of them. So one is the Aviso data set. So the Aviso data set simply is an oceanographic velocity data set, which we often work with in our research group. So this Aviso folder actually contains a bunch of other files. So there's like this Aviso_raw file and this Aviso file. So what it is Aviso_raw file is essentially the raw file. Now the Aviso data, the raw Aviso data generally comes with time resolution of 7 days. So basically you get one velocity snapshot. So a snapshot of the velocity field every 7 days. What I generally like to do is I like to interpolate to a daily resolution. And that's why I store this this processed data set. It's not really processed in a sense that I'm not doing any filtering. I'm just simply interpolating the data set to a daily resolution. And that's what I have here. So that's aviso.mat file. That's the final data set, which is essentially this original data set, however, interpolated to a daily resolution. Now, this interpolation step and is explained in this notebook here, which is called Aviso. So this notebook also introduces and explains the Aviso data set. Now we will generally be, so the data set I downloaded here is the Aviso data set in the Agulhas region. So the Agulhas region is a region close to South Africa, basically. Now, one general thing that one has to keep in mind when working with these oceanographic data sets is that it might be that the velocity field you download is given in meters per second. However, the domain is given is latitude and longitude, so it's given in degrees. And the time domain might even be in days. So you have basically the velocity field, which is given in meters per second, a time domain, which is given in days, and a spatial domain, which is given in degrees. So as you can imagine, that's a problem because you have a unit mismatch. So of course you want that all the space units and all the time units have the same. So all the space and time variables have the same units. So you would need to then convert these units. So you need, for example, to convert the units of meters per second to degrees per day. Now, I have included an additional script. Sorry about that. I've included an additional function, which is called convert meters per second to degrees per day. What this function does, it simply takes as input the grid, so x and y, and the velocity field, also gridded. And the velocity field is given in meters per second. And what it does, it simply converts this meters per second into degrees per day. So that's just like some unit conversion. It is important because it happens, at least to me initially, that I once downloaded the dataset from a website and an oceanographic dataset, and the velocity field was given in meters per second. However, the space was given in degrees per, the space was given in degrees. So when I then tried to do the computations, I was get completely strange outcomes simply because I wasn't taking care of this unit mismatch. So one thing that I advise you is to make sure that the units match. This might seem trivial to you, but at least it happened to me, and also to other researchers I know of. So it might be worth checking that the units are really, so that units really match. So let me just simply close these as I open them. So that's the Aviso data set. And you can find more details here in this notebook I opened previously. So this goes, and again, what I do in this notebook is nothing super fancy. It's just simply taking the original raw data and interpolating it to a daily resolution instead of having to do with a weekly resolution. Of course, you can also skip this step, so it's not really essential. You can also work with the original raw data if you're fine with having a velocity field in a weekly resolution instead of daily resolution. Now, of course, I generally assume that the velocity, so what I assume in these notebooks is that the velocity is given on a gridded domain. So it must be evenly spaced in space, but it also must be evenly spaced in time. So that's important. The velocity field needs to be given on a gridded domain. I mentioned it because, for example, in this Beakley folder, I defined the Beakley velocity field. Now, the Beakley jet is, we're dealing with a periodic velocity field here. So let me just open it a bit. Yeah, so that's basically just the definition of the Beakley jet, the velocity field of the Beakley jet. And the important thing is that the Beakley jet is an analytic velocity field. However, these notebooks have been designed for dealing with real-world data, and real-world data is generally not given analytically, but it's given on a gridded domain. So what you need to do is whenever you have an analytic velocity field, you just simply need to sample this velocity field evenly in space and time. So that's essentially what I'm doing here. I'm defining this velocity field, this model for the velocity field. I'm specifying here a bunch of parameters. So these are standard parameters used in various papers, which you can find referenced here. And I'm simply sampling this velocity field at evenly spaced points in space and time. And again, I assume that, so in this case here, so this Beakley jet is a periodic. So we're considering the periodic Beakley jet. Now, the last data set, not delete, sorry. Just shut down. The last data set is a turbulence data set. So it's a 2D turbulence simulation. Now, as you can imagine, this 2D turbulence simulation, I could not store the data set on GitHub. So what you need to do is you need to open this turbulence notebook, and so I essentially had to store this data set on some external external drive. So what I do is I take this link. So I just like copy this link, and I just, oh, sorry about that, and then just paste it. Oh yeah, sorry, I just need to open this one here like this. So let me correct that for a second. I just need to open this link. So if you click on the link, then basically you are redirected to an external folder. This is a polybox folder from ETH, and I stored all the data inside this polybox folder. So there's of course this turb u, which basically contains the velocity field, and this contains the vorticity field. Now we will just be dealing with the velocity field, so it's fine to just take a look at this turb u folder. In fact, if I open it, then you can see that I have a bunch of MAT files. Now, what this MAT files contain is simply contains. So at every point in time, I've got a snapshot. So these separate MAT files just simply indicate the velocity field at different points in time. What I need to do now is explained here. So I just simply need to download them together with the demos, and I need to put all these MAT files in the folder data turbulence. So I just need to put all the MAT files inside this folder. I just need to download them and put them here. Now, I guess this will take some time now, but you just need to download these folders and put them inside this directory. So let me do that now. This will take some time. But if you download them, then you just need to put them inside this directory, and then you are fine. So that's it for the moment. If you have any questions, then feel free to email me. I'm happy to answer these questions, and I look forward to the next video where we start running our first notebooks. As I said, we will be simply dealing with simple computation. So we'll just be dealing with running the velocity, so computing velocity field or computing trajectories for a two-dimensional data set. And the two-dimensional data set we will be dealing with is essentially, so will primarily be the Aviso data set. So initially we would just be focusing on the Aviso data set. Now, thanks a lot, and see you in the next video. So in the next video, I will have downloaded this turbulence folder, and I will have put it inside this data repository.